I'd like to work out for you exercise number 42 from the end of chapter 7. This is a little bit different than the other ones in that we're going to use a conservation of energy approach for this. If you haven't already read the problem, you ought to read it and see if you can make a diagram that captures the essence of what's given and what you want. So I already made the diagram here for you. In the beginning, you're told that you have a slingshot that shoots a pebble up into the air, and that if you pulled the slingshot back 20 centimeters, the pebble goes up 6 meters as a maximum height. And it goes on to ask you in part A, how high would the pebble go if you pulled the slingshot back 40 centimeters? So while there are easier ways to do this, I'm going to do it the long way as an example of applying conservation of energy. We want to remind you that the conservation of energy approach is the way to go in this first one because there isn't anything besides spring and gravity, so there's no non-conservative work. And when there's no non-conservative work, it's best to use the idea that the initial mechanical energy and the final mechanical energy are equal, both in this case and in this case. The energy here and the energy here are not equal, but the energy of the pebble here and the energy of the pebble here has to be equal, and then same over here. And then one last reminder, the energies that we tally in conservation of energy are kinetic energy, 1/2 mv squared, gravitational potential energy, which is mgy, and elastic potential energy, which is 1/2 kx squared. So k is the spring constant of the spring, and x is how much the spring is stretched or compressed. It is mentioned in the preamble to this problem that the slingshot obeys Hooke's law, so this is the way to go. Of course, that really wouldn't be true in practice, but close enough for this illustration. So the plan is going to be this. We're going to use what's given in the first part, that's this information here, to calculate the spring constant of the spring because that's not given. And then we're going to use the spring constant of the spring and the information for part A to calculate the height if you pull it back twice as far. There's one little trick in here that will come at us a little bit later, and that is the authors don't give us any idea about the mass of the pebble. But we'll see if it matters, and if it does, how we can work around. So I want to reiterate that the initial energy in this particular case is always the sum of any kinetic energy plus any gravitational potential energy plus any elastic potential energy. And I'm looking, here is the initial, and here is the final. So I look at initially, and I see that the pebble starts from rest. So because of that, the initial kinetic energy is 0. Additionally, if we measure the height always from the starting point of the pebble, then the pebble doesn't have any gravitational potential energy because I'll call this spot the y equals 0 level, right where the pebble is at the start. So as a consequence, the pebble doesn't have any gravitational potential energy. And the only form of energy in the system is the potential energy stored in the spring, and that's equal to 1/2 kx squared. So let's hold on to that for a minute and check what we know about the pebble in the final configuration. So the final configuration, the pebble could have kinetic energy, it could have gravitational potential energy, and it could have elastic potential energy. But let's check to see which of these it has. Well, again, at the maximum height, we know that the pebble isn't moving, so still no kinetic energy. There was some in the middle, but it's gone now. There does seem to be some gravitational potential energy because the pebble is no longer at its starting height. It's up much higher. It's up 6 meters higher. We'll use h for that. And there's no longer any elastic potential energy because after the spring shoots the pebble, the slingshot's not compressed anymore. So in this particular case, the elastic potential energy is 0. And all we're left at is the energy in the system is in the form of potential energy stored in gravity. And because of the conservation of energy principle, these have to be equal. So that tells us that a truth of this arrangement is that the initial potential energy stored in the spring is equal to the final potential energy stored by gravity. Now, I wouldn't encourage you to simply jump to this point at the beginning. I would encourage you to go through these steps of evaluating what forms of energy are present, because in different situations, you'll end up with different results. But this is the answer to our problems, and here's how it might go. In order to answer how high the pebble is going to go here, we would need to know the spring constant of the spring. Well, we can get the spring constant of the spring from the first step because we have how high it goes, but there's one little problem. It seems that we need to know the mass, but the mass isn't given. So I'm going to give you a trick here if you don't want to do things out totally algebraically. If you feel like you need the mass, but you aren't given a mass, then you're totally free to make up one. And it doesn't even matter what you make up, because if the mass doesn't matter, it really doesn't matter. So how about we just agree, for the sake of argument, that the mass of the pebble is 50 grams? And then we can proceed. So in the first part, we're going to solve this thing for K. So I'm just going to do that quickly in my head, and then you can pause the video and do it yourself. But if I do it, I get 2 mgh divided by x squared. So that's if I solve this for K. And if you plug in the numbers, paying attention not to make the rookie mistakes we've talked about in class. One rookie mistake would be to not use mass in kilograms, and the other rookie mistake would not be to use the height or the stretch of the spring in meters. But I think if you don't make any rookie mistakes, you end up with a spring constant for the spring as 147 newtons per meter. I calculated that out ahead of time, obviously didn't do that in my head. But you can pause the video and try for yourself until you get that. Then finally, the answer to part A is, how high does it go if you pull it back twice as far? So all of these things would be true, and this result is still true, so we don't have to reinvent the wheel here. We just need to solve this equation here for height and use the K we just got. So if I do that, I get that the height you can check my algebra, but I think that works out good. And if you plug in the numbers that we have here, I think you end up with 24.0 meters. So just before I say goodbye here, I'll leave you with two parting thoughts. One is, notice how this height compares to the original height. The original height was 6 meters, so the pebble went 6 meters high if you pulled it back 20 centimeters. But if you pull it back 40 centimeters, which is twice as far, then the pebble goes 4 times higher. Notice that this is equal to 4 times the original 6 meters. The reason for this is that the potential energy of a spring is proportional to the amount that you stretch the spring squared. So if you double the stretch of the spring, you quadruple the energy stored by the spring. And it turns out the mass doesn't matter at all, at least not in the context of this problem. Notice that when we calculated K here, we multiplied by our made-up mass, but when we calculated our new height, we just divided by our made-up mass. So once we multiplied, once we divided, so no matter what you make up for the mass, you get the same answer. In fact, arguably the easier thing to choose for the mass would have been to simply use 1 kilogram, even though it's not a realistic mass, would give us an answer pretty quickly. Now there is a part B to this problem and a part C, which asks you to calculate the same sort of thing under different circumstances, but I'm thinking that maybe you can start with what I did here for A as an example and try them yourself.